This video is for Lesson 11-3, Proving and Applying the Congruence Criteria. Our learning goals are to prove the congruence criteria and to use the congruence criteria in proofs. So in the previous lesson, we came up with some criteria, but we didn't actually prove step by step with justifications that those things like SSS or SAS were true. We're going to do that in this lesson. You can use the SSS, SAS, or ASA congruence criteria as shortcuts to show that two triangles are congruent. But in order to prove why these criteria work, we have to show that they follow from the definition of congruence in terms of rigid motions. So number one, let's justify the SSS congruence criterion using these two triangles. So we have triangle ABC and triangle DEF, and notice how we have those three pairs of congruent sides, which is the SSS situation. Question A, what given information is marked in the figure? So we have that AB is congruent to DE, and we have that AC with the double mark is congruent to DF, and we have that segment BC with the triple mark is congruent to segment EF. It has a triple mark. Question B, based on the definition of congruence, what do you need to do in order to show that these are congruents? We have to find a series of rigid motions that maps triangle ABC onto triangle DEF. Question C, it is given that segment AB is congruent to segment DE. That's the single marks there. What does that tell you? Well, if those are congruent, what that tells us is there has to be a series of rigid motions that maps segment AB to segment DE. So question D, draw a figure to show the result of the sequence of rigid motions that would map segment AB onto segment DE, and assume that this sequence does not map point C to point F. So think of it like this. We have these two original triangles at the top of the screen. If we were to locate a point right there along this segment that would connect B and E together, and then rotate that triangle 180 degrees, it would create this picture here with the green triangle and then the new triangle ABC done in green. Notice how segment AB is lining up perfectly along segment DE. We've mapped AB onto DE. That proves that they're congruent. Which points coincide in our drawing? Well, point A coincides with point D. Point B corresponds with E. And it also asks what segments coincide. Well, this one right across the middle here. Segment AB coincides with segment DE. Question F. Mark the line segments that you know are congruent in the figure. We knew that that was congruent to that this one was congruent to this, and because these coincide, I'm going to mark them using that sort of a symbol. That was our SSS situation. Question G, based on the figure, how is segment ED related to segment FC? So ED runs across here, and FC is running vertically like this. These are crossing at a 90-degree angle, and it's being split into equal parts right there. So segment ED is the perpendicular bisector of segment FC. And I know that because E and D are equidistant from F and C. Question H. Consider the reflection of triangle ABC across segment ED. What is the image of triangle ABC? So this is saying if we take triangle ABC, this bottom triangle, and we reflect it over that line, which was the perpendicular bisector, it would make that top triangle, triangle DEF. How do you know? Because point C will map onto point F. This argument in item 1 shows that a sequence of rigid motions maps triangle ABC to triangle DEF. Specifically, the sequence of motions is a rotation, right? We talked about that. Locate the center of the rotation exactly in the middle between those two dots, that corner and that corner, and then rotate it 180 degrees. Once you have the triangle here, you can then reflect it over ED, and it pops up and would line up perfectly on triangle DEF. So by definition, those triangles are congruent. Number 2, in the proof, is it important to know exactly which rigid motions map segment AB to segment DE? Well, the answer is no. We don't have to know exactly what the rotation is that swings that triangle around to get it to line up perfectly on that. But if we do know the exact motion, that makes the proof make more sense. We're going to skip number 3 here and move to number 4. To justify the SAS congruence criterion, use these two triangles below. Notice that this time, instead of having marks on 3 sides, matching up to marks on those 3 sides, we have the SAS situation. So question A, what given information is marked? We have that angle A is congruent to angle D, right there. We have that segment AB is congruent to segment DE, that one right there. And then the double marker, we have that segment AC is congruent to segment DF, that one right there. So question B, the proof would begin in the same way as item 1. Since we know that these segments are congruent, since we know that that segment is congruent to that segment, that means there has to be a rigid motion or a series of motions that would map that onto that. And it's going to be the same one as before. If you find a center right between that corner and you swing that around 180 degrees, it would create this picture with the green triangle. Gosh, I said that wrong last time, I think. With the purple triangle, and then our new triangle ABC shown in green. Mark the line segments and angles that you know are congruent. So from our original situation, we knew that segment AC was congruent to DF. We knew that angle A was congruent to angle D. And then the side here that coincides, I'm going to mark that those were congruent with that symbol there. Question D. Suppose you reflect triangle ABC, the green one, across segment ED. What is the image of segment AC? So if you take that segment and you flip it to the other side, there's its image, segment DF. And the reason is because segment ED is the angle bisector of this angle. Because segment ED runs right across the middle of the angle, when you flop that over to the other side, that segment would land perfectly on that segment. When you reflect triangle ABC across segment ED, can you conclude that the image of point C is point F? Can we conclude that that point would reflect and land onto point F? And the answer is yes. Because CA, this distance here, is equal to FD, this distance here, we know that point F has to be the same distance from D as what point C is from D. And that means that F is the image of C. This argument in item 4 shows that there's a sequence of motions that maps the triangle onto the other triangle. That means that they are congruent. Okay, next one. Let's justify the angle-side-angle congruence criteria. Let's use these two triangles. Notice what's been marked as given information fits the ASA situation. This angle congruent to this side congruent to this, and then angle B congruent to angle E. What given information is marked? And I just identified that. Question B, the proof begins the same way as the other proofs. So again, imagine that that first thing is that rotation that moves triangle ABC into this position. Question C, mark the line segments and angles that we know are congruent because we were given that they were congruent. So remember, angle A was congruent to angle D, so we can mark those. Angle A, angle D get the same kind of loop in them. Angle B and angle E, double loops. And then that side there and that side there are congruent, and here they're shown as actually overlapping each other. I'm going to mark them with that symbol. Suppose you reflect the green triangle. Hey, I said it right that time. Across segment ED. What is the image of AC? What's the image of this side when you pop it across there? It would be segment DF. What is the image of BC? So this segment here, what's its image when you pop it across there? It would be EF. In our reason, because segment ED, so because this is the angle bisector of that angle and that angle, that's why I know that these things match each other. When you reflect triangle ABC across segment ED, can you conclude that the image of point C is point F? Can we conclude that the image of that dot is that dot? And the answer is yes. The argument in item 5 shows that there is a sequence of rigid motions that maps the triangle onto the other triangle. It was first a rotation and then a reflection. Because there is a sequence of transformations, then by the definition of congruence, those triangles are congruent. So now that we've actually proved with finding sequences of motions, we can now use SSS, SAS, and ASA congruence criteria to prove that triangles are congruent. We thought we could do this after yesterday's lesson, but here we've actually proved them by finding rigid motions. Now, example A, Greg knows that point X is the midpoint of segment JK. Because point X is in the middle between J and K, we know that that is congruent to that. We can conclude that. He also makes measurements and finds that JL is congruent to KL. So JL, that one, is the same length as that one. He must prove to his boss that triangle JXL, so this triangle on the left, is congruent to triangle KXL, the triangle on the right. Here's our given information, copied down again from what we had read there. And here's what we're trying to prove, that the triangle on the left is congruent to the triangle on the right. And you see the statements and reasons already filled in this example. So it's been a while since we've done these 2-column proofs, several lessons ago, but let's think back to how they begin. You always start with something that's given to you. Here was one of the given statements, that X is the midpoint of JK, and the reason is it's given. From that, we can conclude that that length equals that length. I had already marked it in the picture, and here it is written in the proof. The reason is the definition of midpoint. The other thing that was given to us, which I had marked with the double marks, was that JL was equal to KL. That was given. Remember how earlier we had overlapped one side of a triangle with another, and we had marked that they were congruent to each other with that symbol there? And that's what this statement is saying, that segment LX is congruent to segment LX. Segment LX in the left triangle is congruent to segment LX that's in the right triangle because they're the same segment. And our reasoning for making a statement like this, where the left side and the right side are exactly the same thing, is called the reflexive property. That was something from algebra class, the reflexive property. Congruence is reflexive. Looking at this picture, we have the side, side, side situation, right? When all 3 sides of one triangle are congruent to the 3 corresponding sides in the other, we can say that they're congruent, and our reason is SSS. We're now able to use SSS as a reason because we proved that it was true. The other ones that we can use for reasons after today's lessons are ASA and SAS. We haven't yet proved the one from the other day called angle, angle, side. We haven't proved that that's true. We think it's true because of yesterday, but we can't use that as a reason yet until it's proved to be true. Here's some try these problems and some check your understanding problems, so I'll pause the video. In this lesson, we took 3 out of the 4 congruence criteria from yesterday's lesson and proved that they actually were true by finding a sequence of rigid motions that mapped one triangle to the other. And because we had proved that those were true, we were now able to use those congruence criteria in proofs.